Hi everyone, I'm Patrick, and in today's video you will learn how we can deploy PyTorch models on iOS devices, and we built a small mobile app to do image classification. So this is the app we're going to build, and in the first part of this video you will learn how we can optimize our PyTorch models for mobile using Torchscript. And then in the second part later you will see how we build a small iOS app in Swift and then integrate our model. So since I'm not the most experienced one in Swift, I'm really excited that I got help today from Kevin Kromik. Kevin is a senior iOS developer, and he also has his own YouTube channel where he teaches about software development, and he makes cool videos about his daily life as a software engineer. So I'm really happy that I got help today from him. And of course, if you want to check out his channel, there's a link below the video. There will also be a video on his channel where we talk together about AI and machine learning in general. So this could be interesting to you. And now let's jump to the code. All right, so as I said in the first part, we learn how we can create optimized models with Torchscript. So with Torchscript, you can create serializable and optimizable models that can then run in standalone applications. So they don't have to be written in Python. So for example, you can integrate this in C++ applications or iOS, Flutter, and Android apps. So even if you're not interested in iOS development, you should still learn how to optimize models for deployment with Torchscript. And it's actually pretty simple, and I will show you what you have to do in a moment. So the app we're going to build is a simple image classifier that classifies dogs and cats. So this is a very popular dataset on Kaggle, and you can download it. So I recommend that you do this now. So I already downloaded the data, and now we also have to reorganize our folder structure a little bit because we use the image folder from Torch Vision to load the data. So for this, you want to create a folder named data, then two folders, one named train and one val for validation. And then inside each of them, you create a folder cat and a folder dog. And then you want to copy the corresponding images into this folder. So some cat images into the cat folder and some dog images into the dog folder. So one for the training and one for the validation. So after you have done this, you can use the code. So here we use a transfer learning approach where we use a pre-trained model. And I already explained this in this tutorial that I can link here. So we use almost the exact same code. So you can find the code also on GitHub, and I will go over this only very briefly now. So the first thing we have to do is to create transforms for the training dataset and for the validation dataset. So for training, we apply random rotation, random flipping, and also random cropping and resizing. Then we transform it to a tensor, and then we normalize it to these values. So these are taken from the same values that the pre-trained model has used. So it has to be those values. And now for the validation data set, we don't have to do these random transformations, but we still have to resize it to this format. So the images have to be in the size 224 by 224. Then we have to convert it to a tensor, and again we want to normalize. So these transformations here are important because later we have to apply the same transformations in our iOS app. Then we create two data sets, so one from the training image folder and one from the validation image folder, and we also create two data loaders. Then we can define a device, so if we have a GPU available, we can use this. Then we define one function to train our model. So here we iterate. So we say for epoch in range num epochs, and then we do our typical training thing. So we also iterate over the data loader. Then we push our tensors to the device if necessary. We call optimizer 0grad. We call the criterion and calculate the loss. Then we call loss.backward and optimizer step. And then here we also apply a scheduler, and then we save our best model. So again, you can find the code on GitHub, and I explain it in the other video. So this is the exact same code. And then, so after this function, now this is the only thing we change. So here we use a different pre-trained model. So in the other one, we used the ResNet, I think. And here we use the MobileNet version 2, which is smaller and perfect for mobile deployment. So you want to load this and say pre-trained equals true. And here we only retrain the last layer. So we set all the parameters to require scrut equals false. And then we create one new linear layer with two outputs because we have cats and dogs, so two classes. And we apply this as our last layer. And then here we define our entropy loss, our optimizer, our scheduler, and then we put everything into our function and train this. So after training, you can also save this. So again, this is the exact same code as last time. And this is basically everything you need to do to create a transfer learning approach and then build your model to do a cats and dogs classifier. And now let's see what we have to do after training to use Torchscript and optimize our model for mobile. So to optimize this for mobile, we say from torch.utils.mobileOptimizer, we want to import optimize for mobile. And now what we have to do is basically we have to do one forward pass through our model and keep track of all the operations that happen. So we also call this tracing. And for this, we need a mini batch with only one example image. So we could use one image from our test images, but we can also just create a random tensor by saying torch.rand, because the values are actually not important here. So only the correct shape is important. So for the shape, we use 1 for one sample in our batch, then 3 for 3 color channels, and then 224 by 224 for our image size. And now let's pass this to our model. So before we do this, let's actually push our model back to the CPU. So we say model conf equals model conf dot to, and then to the CPU, because we can't really use the GPU on the iOS device. And now we only have to do 2 steps. So we trace and then we optimize. And for tracing, we want to call torch.chit.trace, and we have to give it the model and then our mini batch, so our example tensor. And this will give us back our traced module. So let's call this traced module equals this. And now we only have to optimize this. So let's call this optimized underscore model equals, and now we use this function that we imported. So optimize for mobile, and this needs the traced module. And now this is all we need to do. So now we can simply save this. So like here above, so here we save the normal model. So let's do the same thing. And for the path or the model name, let's simply call this model. And here, instead of saving only the state dict for the optimized model, we can actually save the whole model. So we can say optimized model.save path. And now this is everything we need. So now we can run this and see if this works. All right, so this worked, and now here we have the original model and the optimized model, and now this is what we have to give to Kevin, and then he can integrate this in the iOS app. And if you also want to use this again in a Python code, what you can simply do is you can say model equals torch.chit.load and then the path name, so from this, and then you have the model, and then you can just use this like a normal PyTorch model again. So yeah, that's basically everything we need to do. If you have a model and want to optimize this with Torchscript, you import optimize for mobile, then you need one mini batch with the correct shape. Then you call torch.chit.trace, and then you call this optimize for mobile function. Then you have your optimized model and then can simply save this and reuse this. And now let's see how Kevin integrates this in the iOS app.
Let's get started by creating a new Xcode project. Let's call it, I don't know, PyTorch demo. And as an interface, we are selecting here storyboard. If you're familiar with Swift UI, you can also select that. I prefer storyboard at the moment. Now we have to move to our terminal and install CocoaPods. That's our dependency management tool. This might take now a while. Now we have to go to the root of our project and initialize our dependency. We do that with pod init. This will create a pod file, which we have to open with a text editor of your choice. And here we have to insert our PyTorch dependency. We save it and we initialize our workspace. We do that with pod install. With pod install, we are installing the library, the dependency PyTorch, and it will create a workspace for us. We have to open that workspace. It's this file here. To make our dependency work, we also have to include some bridging files. This is needed because we are using Swift as a programming language, but the library is not written in Swift. You can either find these files in the documentation of PyTorch or take it directly from our source code that we uploaded here in our project. To be more specific, we need these Torch module files. We basically just drag and drop them into our project. And as we are importing non-Swift files, it will ask us if we want to include or create a bridging header, and we have to say yes. To organize this a little bit better, we can now select all of them and create a new group, and we can call this Torch module, for example. In our next step, we have to import a model file that Patrick already prepared for us. Make sure that you add it to our target. PyTorch also needs a text file where we have listed all the elements that the model can predict by name. In our example, we have cat and dog, so we have to write that into our text file. We also import this file, and as you can see, we only have two words, cat and dog. So let's get started with our UI. Therefore, we have to open the main storyboard. We have our main view controller, which is empty at the moment, and we have to insert first a label where we display the actual result, and a UI view. This UI view will host our preview of our video feed. In our next step, we have to create outlets into our code, which means they are references, so we can use these elements that we created now in our interface builder in our code. So you just have to select the element that you want, hold the control key, and create the outlet into our code. It's that easy. So here we have our result label. And the same we want to do with our preview. In our next step, we have to create a predictor. This is basically just the interface which loads our model and communicates with PyTorch. So we create a new Swift file. We call it predictor. And a new struct which holds our result. Each result has a label and a score. The label is actually the name of the result and the score is the probability. Our first function, topk, just takes the results and combines the score with the label and returns all the results in an array. To make sure that we don't run multiple predictions at the same time, we need to have a local property called isRunning. Furthermore, we need to initialize our module, which is basically loading our model file from our bundle so we can use it in our predictor. This method is very simple. So we are loading the file path from the bundle main, which is the main bundle of the application, the path, to the resource file model, and the extension is PT. With this path, we are initializing our Vision Torch module and we return it. With our labels file, we do exactly the same. The actual prediction happens now in our predict function. This takes as an argument the buffer, which is our actual image. First, we have to check if a prediction is already running. If so, we return nil, which means that there is no current prediction. If we are not running, then we have to say, okay, now we are running. This is just needed because if the buffer keeps pushing new images, the predictor is overwhelmed. Arguments in Swift are immutable by default, so we have to create a temporary property. In our next step, we are doing the prediction by taking our module, calling the predict function with the image argument, and we are feeding our buffer. Now our prediction is done. We say it's not running any longer. And we take now our output and convert it in our inference result so we can display it in our application. Now let's go to the UI. First, we have to configure our camera. As the camera is part of the AV Foundation framework, we have to import that first. We are creating the camera by calling the AV capture device. Using the default, we say we want to have the built-in wide-angle camera for video, and the position is the back camera. We also need a new capture session property where we hold a reference to the capture session itself. We create the input so we can capture the content of the camera. As we also want to see something, we have to configure now the preview. Therefore, we need a new property, which is the preview layer. For this, we are basically just taking the capture session and feeding it into our preview layer. So we have a UI reference to our preview. And we created already earlier our preview view, which is then the one pinned to our main view controller. And we are adding the preview layer as a sublayer, which basically just means we are taking this feed and we pin it into our visible view. In our next step, we have to create the output of the camera so we can do stuff with our video preview. For this, we need a new property, our video output. This can be seen as the buffer. Furthermore, we need 2 dispatch queues. This is just needed for concurrency reasons. So we basically can dispatch different tasks on different queues so they don't block each other. In our configure output method, we are basically just connecting our capture session where we put all the pixels in and we map them to our video output. As iOS is very restrictive, we need to ask for permission to use the camera, and therefore we need this prepare function. This will basically just ask if we are authorized to use the camera, and if not, we have to ask to get access. This will trigger a native pop-up and the user can either decline or accept it. iOS also requires to define a text that will be displayed in this alert, explaining why this application needs access to the camera. This text needs to be defined in our info plist file, and we have to create here a new property called privacy camera usage description. And we need a description which can be, I don't know, needed for live preview. PyTorch needs the image to be normalized in a specific format. Therefore, PyTorch also offers a file to normalize these images. For more details, you can also read the documentation for that. Therefore, we need to create a new Swift file. We call it pixel buffer helper. And we just copy this entire file. Now there are only two more functions missing. We have to capture our images and feeding it to our predictor. And the last step is to interpret these results and display them in our UI. So to retrieve the frames, we need to write an extension because we need to conform to a protocol. And the protocol is called AV Capture Video Data Output Sample Buffer Delegate. And we have to implement the capture output function, which is part of that protocol. First, we have to retrieve our pixel buffer. Then we have to use our new normalization function and use the pixel buffer, call the normalization function, and we have our normalized buffer that can now be interpreted and used by our PyTorch library. For that, we need a new method called process. This function takes the buffer as an argument. In our capture output function, we are calling this method and we pass our normalized buffer. First, we have to unwrap our buffer to make sure that there is no nil value. And of course, we need a property with our own predictor. We are using this predictor now to predict our pixel buffer. And we pass our result count 2 because we only expect to have either cat or dog. And this will be our result. The result array is always sorted by the highest probability. And as we only want to display the most probable result, we take our first item and the label, which is the given name. Now we only have to connect our result label text to our actual result. So we call the result label, set the property text to the result. Now that all methods are in place, we have to connect them and initialize the session. Therefore, we are creating this new method start session. We initialize our capture session. And within our session queue, we run asynchronously the session task. We have to begin our configuration. We do our camera input configuration, camera output configuration, and we commit our configuration. And we have to ask for permission with our prepare function. Now in our viewDidLoad, which is the method which will be called once our screen gets loaded, we have to start our session. This will only happen once. Now we are finally done and we can test our application. I can test the application with my own dog, but I'm sure some of you might have a cat at home, so you can test it as well.
Now, isn't this great? So maybe it's also worth mentioning that we didn't show Kevin's dog to the model while training it, but now it can still correctly classify it. And yeah, I hope you really enjoyed this tutorial. And again, thanks to Kevin for helping me out here. And if you're interested in his channel, check it out. And then I hope to see you in the next video. Bye.